Welcome, AP Stats. This is Coach Jay, and namaste, namaste. This is our last for a test before our final. I am so excited. Your hard work, your enthusiasm, your energy is paying off, and I really do appreciate that. I know this. I feel better about Chapter 7 than I have on 5 and 6. 5 and 6, probably the most difficult tests that are out there. I really feel good on 7-1 and 7-2. Really dial in off the homeworks, the review, the check your understandings, the golden nuggets. Make sure you are really focused in. There's not a whole lot of material, but the material that is on there is very, very important. Before I go, inaugural shot. Oh, very close to having back-to-back days, but not quite, not quite. All right, let's do this. Let's go to our – oh, I have a wrong side. There we are. Come over here. I'm going to bring my flip chart over. Before I do this, do not make fun of me. This is my high school photo. So when I show this to you, I apologize. This was me in high school. Yeah, I know. I know what you're thinking. Why? I don't know why. Unfortunately, yes, I did take this. This was my picture that I took of myself. And why, I have no idea, but there's things that we regret in this life, and this picture is one of them. But I wanted to share it with you largely because I have no idea why I did. I know that people are going to make fun of me even more so than they do now, and so thank you from the bottom of my heart. All right, so with that being said, I wanted to start off with this Define Me section, just so you know what's over this podcast. I want to start with this. I've got literally 30 minutes left until my next class comes in. It's actually, if you're in my 7th period, you're going to be coming in here shortly. So I do want to go over a couple things. I may hit on a couple of these off the homework from chapter 7.2, and so I might hit on a couple of those to make sure we're good. We're also going to hit on some of the concept lists that's here. And then from Friday, you're going to have this for Friday that I'll give to you for the review, and some of you already have this, and you could kind of look at this as you go. The answers are posted online, and I really go through these in more detail from last year's podcast. So if you wanted to check that out, you definitely could on what's expected on some of these. And so we can definitely look at that if need be and go from there. Question 9, you could throw out question 9 just as a heads up. That one is not off the test there, and so yeah, we could definitely look at that next semester, but not today. So let's go over some of these questions. Maybe this podcast isn't as exciting as before because I'm not really going through problems. I'm more going over concepts, and I just really want to get your feedback on what's the most beneficial thing for you. And so let's just kind of start from the top, or maybe we'll start from the bottom. We'll be there. Okay, we'll start from the bottom, then all of us as a team will be there, and then we'll work our way up. All right, here we go. What is one thing you're confused on? This right here, this question is one in which I would say if you are confused on a specific topic, prior to the test, I would say coming in the morning, if I'm not here on Monday, by the way, I'm not going to be here on the day of the test, so shoot me an email, whatever that looks like there, and I'll do my best to try to answer them in a timely manner. Let's talk about this distribution idea. A distribution is something, it is a display of our data. This allows us to look at things like socks and look at things that maybe relate to each other in terms of spread, outlier, center, and shape. That's really what we look at within a distribution. Many of the distributions we look at are display the data. Other times it's a dot plot, especially within the activities we've had in class recently. Variability is important. Variability is the spreading out of data. This could be range, it could be IQR. Traditionally, we have standard deviation that we like to use, which is the average distance from the mean. But that is a huge, huge part of not only this semester, but this chapter. Remember, with variability, how can we, the ideal thing to do is to lower variability. And to lower variability, we have to increase little n, which would be my sample size. So the higher the sample size in which I select, the lower the variability that would be there in terms of approaching my true mean or true proportion that we've got there. All right, a sampling distribution is a sample of a sample. We remember this. Remember when we had dots and we looked at Reese's Pieces? Reese's Pieces? I can't say it. I'm sorry. I'm sorry. One of those things. Where we said where each dot, what does that represent? Each dot represented, we'll do the proportion one, a p hat of the proportion of orange in one sample of size, I think we did 50. We'll just say 50, where little n was 50. Remember, if I were to increase this 50 to 100, we would expect this data to really just push in on either side. It would, and I'm actually doing it with my hands, by the way. You could do it as well, but it's decreasing when we increase that sample size. The population distribution means that the whole population is placed in a display of data. An example of this would be if I took, each dot would be representative of one specific item within my entire population. So if I was to do the population distribution for grades within all of AP Stats grades in the entire world off of chapter 6, we would say every dot would be one specific grade. That is a population distribution. The same holds true if I took a sample distribution and I got a sample from all of the population of grades of 70, 80, 62, 98, and 101, we would say that those 5 grades would then have 1 dot for every value. Whereas over here, each dot is a proportion of a sample that I selected. And we remember that is a sample of a sample is a sampling distribution compared to 1 dot representing each of these, which would be a sample distribution. Okay, that's a difference. Now, how do we get low bias? There's a couple things. First of all, we have to sample well. And we know what that means, right? Randomly, where it has no bias in how I selected the data, making sure it's representative of my population. That's very, very, very important. But also, how do we get low bias? I would say that low bias would be where the true mean or the true proportion, right? So these are kind of going down below. I apologize. So let me hit this first. A statistic is a number of a sample, right? An example of this would be X bar, P hat, or S of X, which would be the sample standard deviation, right? But each value, the actual number is a statistic, but it's a number of a sample. A parameter is a number of a population. Remember that when we talk about estimations, sample estimates or statistics estimate parameters. We use samples to estimate my population. So the actual numbers of this would be mu, p, or sigma, right? So this is representative of my population. So we call it a parameter. Normally we don't have these. So that's why we've got to use statistics to what we call estimate my parameter. And that's why we use statistics to do that from our sample. When does a sampling distribution have no bias? It's pretty simple. It has no bias when X bar is equal to mu. When they're actually equal to each other, or when P hat is equal to P, or when S of X is equal to sigma. Now, is that possible? Yeah, kind of. It's possible. It's not likely. So it's almost impossible to have no bias. So it's almost impossible to have no bias. But our goal, like a tangible goal, is to have as low of bias as we possibly can. So the closer that X bar estimates my true mu, parameter, right, then the lower the bias will be. That's my ultimate goal there. So how do we get low bias? We sample well so that when we talk about mu, we have X bar that is close to, usually is not equal, but close to my true mean. Same thing holds true for p hat, okay? And the same holds true for when we're talking about standard deviation, right? We use the statistic to estimate my true parameter, okay, of my population. Let's look at the 10% condition. What is it? Why do we use it? Remember, the formula is little n is less than or equal to 1/10 of big N, which means that my sample, and I would actually plug it in. Let's say my sample was 50, was less than or equal to 1/10 of, say I chose it from 1,000 of my population. If this is true, then it can kind of override independence. All right, really listen to this. I'm not going to write this down, but it means my population is so large that when I choose something from it, I don't actually have to replace it because the percent that it would change would be so small it doesn't even matter. So it doesn't have to be independent for us to estimate this, but we use it to be able to show or overcome independence. That's the key word, independence. The central limit theorem is kind of the same thing as law. Well, it is the same thing as law. Important. There's one question off of your test like this. Just remember that these two are the same. Remember, what does that mean? That means that n is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. If these two things are true, which we'll actually show, so let's say, I think it was this for like 0.4 for the Reese's Pieces. I know y'all are making fun of me. It's okay. I'm secure. So when I plug this in, since both are greater than or equal to 10, we can then say that we can approximate what? Approximate my sampling distribution. That's what we're talking about. As normal. As normal. Okay, and that's very important when we're going forward with this. Another note that I need to just share with you is we have to show independence or the 10% condition, right? Because that's why we use this if independence doesn't exist. We've got to show this in order to use our standard deviation formula, okay? Which we'll talk about. Or you could look at, if you're looking at this, section 7.2 is what we're focused on. But we've got to show this before we go to our standard deviation formula, okay? And there we go. Yeah, changing samples into a proportion. I remember this. If you got 20 oranges and you selected them out of 50, then my proportion, so by the way, this is not a mean. This was just what I sampled from. My p hat for this would be 20 out of 50, which would be 0.4. Okay. So just as a reminder there. These are just good things to just remind ourselves on as we're progressing forward on it. And just some things that I wanted to remind you of. Now, as we go, it says, which of the following are the mean and standard deviation of the sampling distribution of the sample proportion? I don't know if I gave that to you. Oh, that's really weird. I don't know if I gave it to you off of 40. Is there one that I missed? I might have missed parts of that. So I'm just going to nix that one to go over. Look at number 44, though. It says decreasing the sample size from 750 to 375 would multiply the standard deviation by what? Well, let's just look at the equation. The standard deviation of the sampling distribution of p hat. Okay? We're going to have two of them because I'm changing it from 750 to 375. This would be the square root of p times 1 minus p divided by n. So this is whatever p is, does not matter. The bottom of this would be 750. On the other side, I would have p times 1 minus p, and that would be the same, right? The only thing I'm changing is to 375. And so when I change this, what is happening to decrease the sample size from 750 to 375? Well, just trying to see here. So literally this would be the only difference on this. So I'm going to take this and this out. So the bottom part, as we look at the difference, would be the square root of 1 over 750, right? Where over on the right side, this would be the square root of 1 over 75. What did I have to multiply by? By what to get me to 1 over the square root of 375? So what would I have to multiply this by to get to the new one? And so that's kind of the key. Well, this is half of this, right? So I would have to multiply this by 1/2 here, right? So really what you're doing is you're really multiplying this by 2 at the top, but it's inside of a square root. So if I multiplied, again, this has got to be inside of a square root in order to keep it in that square root as we go to the right. But if I multiplied the top by 2, right, that would be 2 over 750, which would be 1 over 375. So really, because this is a 2 inside the square root, I'm just multiplying this by square root of 2. All right, so square root of 2 times this over here would actually then decrease it to square root of 1 over 375. All right, the 45, the sampling distribution of p hat is approximately normal if blank. Yeah, I would say right, this isn't true. Yeah, that doesn't matter. No, that doesn't matter. There are at least 7,500 Division I college athletes. That doesn't really matter either. It's really from the n times p and n times 1 minus p, which is our central limit theorem or law of large counts, depending on how you describe it, that really defines the fact that we can estimate this with a normal distribution. The next one says in a congressional district, 55%, oh, this is a really good one, of the registered voters are Democrats. Which of the following is equivalent to the probability of getting less than 50%? All right, so first off, we're going to assume that this is a normal distribution. I guess we could show that n times p was greater than or equal to 10 because we show it, but we could trust it. If it was on an F or a Q, we would want to make sure we show it. But we have a sample of size 100, okay? So got that there. So what we've got on this normal distribution is this n comma the mean or the sampling distribution for p hat, standard deviation for p hat because we're talking proportion. First off, we know the mean of p hat is equal to my true p. And our true p was for the population, which would be 0.55. So 0.55 would be my center. And the question was which of the following is equivalent to the probability of getting less than 50%? So less than 50% of the vote, 0.5 here, and anything less than, right? So that would be that right there. So how do I find what the z-score of this is? We remember that z-score, and I'll put it up there, put it up top. Put this in red. The z-score is value minus mean divided by standard deviation. Well, we remember that the z-score, in this case, the value would be 0.5. That's what I'm looking for. And remember, the z-score is going to be not greater than, it's going to actually be less than, because we want anything that is 0.5 or less than 0.5. Minus, what's the mean? It's 0.55. Divided by, and this is the key, what is the standard deviation? Well, the standard deviation for the sampling distribution for p hat is equal to p times 1 minus p divided by n. Okay, so this would be the square root of 0.55 times 1 minus 0.55 divided by n, which would be 100. Okay? little n, right? The sample, not the population. So once I look at this, I can identify, by the way, if I was to show the law of large numbers to approximate this with a normal distribution, I'm assuming it, but I would have to show this, right? That's what I would show. And so once I plug this in, or I could just look down here and say, which would be equal to this? Well, this one would not be. 0.5. 0.55. Well, this is mean minus value, so that's incorrect. Wrong formula here, right? Wrong formula. This would be the formula for a binomial mean. Okay, we're talking about sampling distribution. Different world here, and same here. So I would say this is the right answer once I notice the 1 minus 0.55 is 0.45, and that's how I would solve for the z-score that's there. I can either do z-score on an FRQ, or I could set it up using normal CDF and show it that way as well, okay? But understanding the formula is good in setting us up for doing off of the test. Okay, let's talk about a couple things. Number one, we kind of hit on that already, the correct notation. Number two, concept-wise, variability and bias. How do I, what's the ideal type of sample that we want in terms of sampling distribution to predict our parameters for our population? Our desire is to have low bias and low variability. That's the goal. How do I get low variability? I increase my sample size. How do I create low bias? I sample appropriately, right? We talked about getting low bias in an appropriate manner. Number three, looking at three distributions, comparing variability and various biases. This would be a good example of a sheet. If I have something that looks like this and something like this, and then maybe I have if I said rank these in order, let's say that our true mu is here, and I'm just putting them all at the same spot, okay? Hold that pull. Right here, okay? So here's all our true mu's, and I say, hey, you know what? What I want you to do is I want you to identify for these three, which has the lowest bias. Well, which ones would be closest to my true parameter? And I would say in this example that the best would be this one, then the second, so this would be C, then B, then A, right, in terms of bias. What about variability? Which has the lowest? Maybe this is a bad example. I want to kind of look at this one up here. Let's see here. So this was probably sample. Just use yellow so you're not confused. Okay, to show you the difference. So we would say the lowest variability would actually be A, right? But it has very high bias, very high, because it's way away from my true mean of true parameter of my population for mean on the mean. The next one, I would say the highest variable, or the next highest would be C, and then the third would be B. Now, what would be the best predictor? What sampling distribution would be the best predictor of my population? I would say C, because out of all of them, it would have the best combination of low bias and low variability out of the three of those. So noting that and knowing how to identify. Look at number 12. That was pretty much what I stated here, but identifying and being able to describe that is going to be very important for that first FRQ. The next one is number 4, the sampling distributions and standard deviations. The one formula you'll need to know for the standard deviation of the sampling distribution, p hat, right? Again, this is a statistic, right? We're finding the standard deviation of the statistic, and this is equal to the square root of the population parameter of our proportion divided by times 1 minus that p. and then divided by n. This is on your formula sheet, but remember, we're talking, this means the standard deviation of my sample p hat. This is the mean of the sampling distribution for p hat. That's why there's this like little subscript here. And that equals my, okay? All the stuff from the standard deviation of x bar or the mean of x bar, you do not need to know for this test. That was 7.3, and you're not old enough for that quite yet. This over here was 7.2, with 7.1 being more or less the practice over what is a sampling distribution on that. Number 5, we did that. Number 6, the law of large numbers. This also on number 6, really the 6 and 7. The law of large numbers approximates something as approximate normal. Know the formula and how to apply that. That's very, very, very important. I did want to look at really quick. I'm going to look at this test here. I'm going to give you the central limit theorem question right now. Sound good? So take notes here. I'm going to actually give this one to you. All right, let's see if we got it here because I want to give the exact thing. Remember, the law of large numbers is a big, big part of. All right, you're still on with me. All right, let's see here. Yeah, identifying a statistic and parameter from a situation is very important. All right, so if I say 80% of all GAC students text and drive, we took a sample of 100 students. Out of that sample, 60% texted and drove. The population parameter, right, for our proportion, our regular P would be 0.8 because that's the population. Sample proportion, P hat, would be 0.6. And I need to go over that. I need to hit that. Perfect. We've got that part. All right. Remember that if it fails on the law of large counts, I'm just reading this real quick. The central limit says that when a simple random sample of size n is drawn from any population with mu and standard deviation of sigma, then when n is sufficiently large, the blank is true. And that's where we're talking about something that's approximately normal. So let's just kind of stop right here because this is a good place to just kind of hold and just kind of go over. The law of large counts and the normal, the central limit theorem are talking about the same thing, okay? Here's a side note. In order to use the standard deviation formula here, we've got to show that this is either independent or we use the 10% condition, which says little n is less than or equal to 1/10 of big N. Over here, these two things are talking in terms of the same thing. This approximates, by the way, it's separate from what I just said. This approximates a sampling distribution as normal, okay? Approximates a sampling distribution as normal. And it states this, that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So if these two things are true, then we can approximate with the sampling distribution as, or we can approximate a sampling distribution as being normal. So this is where I could do the normal CDF or z-score, right? This is where in our z-score formula, we get p minus p hat is, and this would be either greater than or less than. I'll say less than because that's normally what we're using z-scores for there. And then it's the square root of p times 1 minus p divided by n. Sometimes this could be greater than if I say what's the probability that it would be greater than 60% or the top 30%. So just be sure that when you do the graph that you highlight the correct area. And we use z-score to find the area of that section, but this would be our value. and I already went through this, but value minus mean divided by my standard deviation, okay? But you got to show this over here in order to approximate it as normal. If one of these fail, here or here, you'll know that in that instance, we're not able to approximate the sampling distribution as normal because our sample size is not large enough or our p proportion isn't closer to 0.5. But if these fail, you know what to state there, okay? Shape is important. Identify the shape. It could be related to this. It also could be relating to, hey, describe this shape. We went over 6, 7, and 8. Random samples of a population. Y'all are getting a treat right now. If you're watching this podcast, you're getting a lot of treats right now. Yeah, man, that's a good one. Knowing skewed left, skewed right. Good night. You need to know that. Approximately normal. If we take yeah, okay. I think we know that one. I'm just reading real quick. I'm not leaving you. Yeah, just remember that if I take a distribution here, right, of a sampling distribution, right? So this is a sampling distribution. I know y'all are coming here in a second. Of P, right, of P hat, then each dot of these is one sample of my distribution. This is our statistic, right? Now, this will vary from my true P, but what we can state is that if we take many, many, many of these, that our center of our sampling distribution should approach my true P. In fact, it should be identical for no bias, but the closer it is, the lower the bias that we get there, okay? And that's what we've looked at there. Numbers 11, look at, I will tell you, number 13, look at 7.2, look at the check your understanding, look at the activity, highlight, highlight, highlight. Got me? Hey, listen, appreciate y'all. Y'all are about ready to come in for class in just a second. I wanted to give you that information. Have a phenomenal day. Be blessed. We'll see y'all.